Okay, so good. So today we are going to talk about what is the color glass condensate. Until now we have been talking about scattering, particle scattering on classical fields or classical color fields. And the color glass condensate is kind of going a little bit more in the direction of where does this classical color field come from? How do we calculate things in this picture? How we got somehow the crucial ingredient is that we need to know where this classical color field comes from. So the color glass condensate is an effective theory for small x degrees of freedom. I'm not going to define an effective theory in the same way as Thomas by writing a Lagrangian. I'm just going to say somehow wave my hands and talk about different kinds of degrees of freedom. So, but as all effective theories, most effective theories, it is nevertheless based on separation of scales, that there are different kinds of degrees of freedom, that we are different kinds of degrees of freedom that are very different from each other, and we are only interested in some of them and less interested in the others. So the degree of freedom here is that we are thinking about a high energy proton or nucleus. It's going in there at high energy traveling, and we want to know what is it. We want to understand the gluons that are the small x degrees of freedom. So we will have two kinds of degrees of freedom: small x, which is a classical color field. So these are small x gluons in a proton or nucleus. And then we have large x degrees of freedom. Which appear, and for the large x degrees of freedom, we don't care whether they're gluons or quarks or anti-quarks. The only thing we care about the large x degrees of freedom are that they have color charge. And this was part of the reason why I somehow introduced the iconal approximation and the iconal vertex. You remember that in the iconal vertex, I claimed that a high energy particle, if it radiates gluons that are very soft, small longitudinal momentum, the only thing these soft gluons care about is the color charge of these particles. They don't care about the spin. They don't care about whether it's a fermion or boson. They care about how much color does this large x particle have. So we are going to have a classical effective theory, and these are the degrees of freedom, the small x gluons that we are interested in, because we are interested in. We have decided that we want to look at high energy scattering experiments where the small x degrees of freedom are important. And the large x degrees of freedom, we want to know as little as possible about them to simplify our life. Okay, so this is the separation of scales, and then there is some scale in between. I can decide that x greater than 0.01 is large x and less than 0.01 is small x, or I can decide on some other value of x that separates them, and then of course I can derive a renormalization group equation that tells me how things vary when I change this cutoff between what I call small x and what I call large x. So that would be the BK or Gimort equation that allows me to absorb, take some of these color fields and absorb more and more of them to these color charges when I want to look at smaller things. Okay, good. So this is our effective theory. These are our two kinds of degrees of freedom. As I said, I'm not going to write a Lagrangian because I'm dealing with classical color fields. So I'm going to jump straight to the equation of motion. I'm going to be doing classical physics. So I will just be working with an equation of motion. The equation of motion for color fields is a covariant derivative of the field strength tensor is the current, right? So these are now, in my notations, these are matrices. So the covariant derivative is d mu plus or minus ig a mu where this A mu is AA and TA. And I like to write things in the, so this is the color A component of the gauge field. This is a fundamental representation generator matrix. And likewise, the gauge field strength tensor is my notations F mu A TA. That this is, so I write these as matrices. You could write out the components. The commutator is, well, the commutator is the commutator in terms of these matrices, which are the matrices, which are the generators. Good. So this is my equation of motion, and this is the equation of motion that I want to solve. There is a small consistency condition that says that the current has to be covariantly conserved. So the current covariant divergence of the current is 0. Now these are color currents, not electron. You're used to electromagnetic currents being conserved. Color currents are covariantly conserved. Yes.
I'm a bit confused with the commutator. How would you, if you got like a derivative, that's not gonna.
So this is a very, yeah. So this is a very abbreviated. This is a very abbreviated notation. When I write, the way I think and the way I write is that I have a. Let me see. I have a commutator. I have a derivative of a commutator of a derivative and some function. I think of these as the acting on some test function like this, right? So then I write this as d mu phi f minus phi d mu f, and of course derivative acting on this cancels this, and this is just equal to d mu phi. Okay, so the abbreviated notation, the derivative part, you should just think of the derivative acting on this. It's useful to. Okay, well, let's not. Okay, good. So here are our equations of motion that define our theory, and now let's start looking at a physical system of a high energy nucleus or proton. So now, just to confuse you, I will change here at this point. I will change my coordinate system and go from plus z to minus z. So yesterday we were looking at a dilute probe scattering of the color field of a high energy nucleus. We had dilute probe going in the plus direction and the nucleus going in the minus direction. Now I'm going to forget about the probe for today, and we will only have the nucleus, and consequently I will want the nucleus to be traveling in the positive direction. Okay, so just everything is switched, plus to minus and minus to plus compared to the two previous cases. So I will have a high energy nucleus. It is traveling at speed of light in the positive, along the positive z axis. So what is its color current? Its color current is going to have only one component, some gauge. Its color current is going to only have a plus component. Okay. Good. So this is our J, and now having this kind of a color current, it is very easy to find a solution to this equation of motion. This equation of if I only a solution, a solution is given if I only have only a plus component of the gauge field, such that in my convention. So what happens is that, let me write such that the transverse Laplacian of the gauge field is J plus Now it takes you a little bit to kind of convince yourself that this is actually a valid solution. So the way it works is that here the mu index only takes somehow this equation you get from the transverse the mu index being a transverse x y index. So then, and the f mu from the f mu nu you only take the derivative. From the f mu nu you only take the di a plus component. So this is the index mu. This is a plus. If you don't have any other components for this gauge, I mean, a lot of the commutator terms, a lot of the terms vanish in this equation. If I just assume that I don't have any other components in my gauge, so this is writing this such an equation. I can writing such an equation. I can easily find this as a solution.
Because you have this current. This is a classical.
This is a classical color current.
So if I would take the hydrogen atom instead of a nucleus, I would like to write a QED current, then you would write so this just a cool circling electron circling.
Yeah. So in the classical current of a classical particle is you can write it as something like this, that it's a d4 x. I think it's
delta 4
delta 4 x minus x of the current trajectory of the current, and I guess then there's going to be
the 4 velocity.
the four velocity. So d x mu over dt. Or maybe with some proper dimension. This would be
summed over all the.
This is summed over all the trajectories of all the charge particles.
And so for this nucleus, we would now think of.
It's a d tau actually.
Yeah, so I guess
It's not a d4x. It's a also the d4x should be a d tau.
d tau, of course, if it's a massive, if it's a massless particle, then you have to somehow reformulate things in a different way because you don't have a proper time. But let's say easiest for a massive particle, which is the velocity.
And it should be a d tau, right? You should integrate over the trajectory parameter because you want this to be a function of x.
Yes.
And the velocity.
Yeah. Okay, like this.
The d4x needs to go because it should be a function.
It has to be absolutely. It is a function of x, like this. Yeah, so this is what a current would be for a single classic, for a collection of classical point charge particles.
And then for this nucleus, I will now take every single fork and glue on.
Yeah.
Multiply with the generator, sum over all of them.
Yeah.
And then that's the classical.
That would be the classical. Yeah. But we're gonna take a little bit of an easier, simpler approach to what this. I'm gonna write an explicit expression for this, at least in terms of a model. So there is a color charge, current of color charge. Okay. Good. So now I start drawing. Let's start drawing pictures. Here is my x plus axis. Okay. And I have a current that only has a plus component. So the current is a vector that is pointing in the plus direction. Good. So then let's go further. We want some more insight into the mechanics of this. I mean, into what this. I want to build a picture of what these fields look like in space and time. So the classical current is pointing in that direction. Also, the next thing I'm going to say is the following. I am going to say that this J plus, first of all, it's going to be kind of, I'm writing this kind of a tilde saying that, one second, tilde saying that it's not exactly a delta function, but something that is very peaked. Okay, so very peaked in a way that one can then discuss further. Yes.
This current J that models our target, right?
Yes, you can think as a first approximation, you can think that it models the valence quarks in the
Sure, but the convention that you used yesterday, have the target going in.
yes, and now I switched convention. Now my target is going the other way around. So all the pluses have become minuses, or the minus become pluses. Sorry for that.
Okay.
Yes, right. So now, yes, the convention is changed. Now everything. Now the nucleus is going in the plus direction. Because I'm not going to exactly quantize the nucleus, but I'm going a little bit towards quantizing the nucleus. Somehow want to move it in the plus direction. Wanted to move in the plus direction. And now we're not really going to have a problem. Same way. Okay. So the next approximation is that this current is going to be a very thin sheet along the x minus direction. Okay. So there's two justifications for that. One is a little bit, let's say, the naive, a little bit more naive one. One is a naive Lorentz contraction. So I'm saying that if I have a object, let's say a spherical nucleus with a radius of 6 Fermi, and I boost it to the velocity of light going in the z direction, it's going to Lorentz contract into a very thin pancake, right? So it's going to be, remember, time here is going up, and so it's going to be Lorentz contracted to very thin, and it's going to go that way. So if I take one time slice, measure it at one time slice, it's going to be infinitesimally thin, very thin. And if it's thin in the t direction, it's also going to be thin in the x minus direction. So that's a little bit more naive explanation for why I assume that this current is very, very peaked in the x minus direction. And the more proper explanation is that this current, the degrees of freedom that this current represents, are high p plus degrees of freedom. They are degrees of freedom that carry large plus momentum, right? So x minus, remember, in our light cone coordinates, x minus and p plus are conjugate variables. So because the current represents very high p plus degrees of freedom, I can assume that they are very localized in x minus. Was there a question?
Sorry, can you repeat that?
So just this is the Heisenberg uncertainty principle. So because the current, I decided that the current is going to represent large x degrees of freedom. So large x meaning large p plus, now that I'm going to the right. So the current, the physics of this current is large p plus degrees of freedom. Because it's large p plus, I can say that I can somehow consider them as being very localized in the x minus direction. X minus and p plus are conjugate variables to each other. This is kind of just a Heisenberg uncertainty principle in light components.
My understanding was that it is the small x part that we were actually looking at.
We will get there. We will. Now we start with the current. We will get to the small x. Okay. So then there's the other approximation that I will make. I will make the approximation that the current does not depend on x plus. Okay. So this is so again, this is a little bit something that we discussed discussed yesterday already, except that we had a different point. This is the yesterday, yeah, and the two yesterday we kind of rugged under the carpet that what was yesterday x minus. So that and we discussed this a little bit. There was a question about this that okay, we argued that okay, it's not, none of this is really going to depend on that coordinate, but yesterday was x minus, now I switched directions. So now it's assuming that the current does not depend on x plus. First of all, note that this is perfectly consistent, or in some sense required by the covariant conservation of the current. So this is perfectly consistent with covariant conservation of the current. The current does not, in this gauge, the current does not change as a function of x plus. I do not have I don't have an A minus field that would color rotate the current. So therefore the current does not depend on x plus. So it's consistent with the conservation law. One could argue about this in some sense one has a similar interpretation in terms of a little bit of a naive a more naive interpretation, which is saying that okay, my charges are traveling at a very high speed, high velocity. So not only they are Lorentz contracted to be very thin, they are also Lorentz time dilated, so that the time evolution that they feel is very slow. It's Lorentz time dilated. So and time here is x plus because kind of they're going in the x plus direction. And there's a somewhat a little bit more similar to this. There's a little bit more detailed argument is that because these are degrees of freedom that have large p plus, these are degrees of freedom that have very small p minus. Right? They have very small p minus, and therefore they are very delocalized in x plus. Anything somehow that, even if there is some internal dynamics going on in the Weyler sector, in the frame that I'm looking at, this internal dynamics is dictated by a very small light cone energy, small Hamiltonian p minus, and because the Hamiltonian, the p minus of these Weyler's light degrees of freedom is small, their evolution in the light cone time is very slow. And if the evolution is very slow, I can just, as a first approximation, assume that they don't depend on light cone time at all. So this, yes.
Sorry, I think you have to pin the video, otherwise.
I think I did pin the. Oh, you might. You might have to pin.
But you're recording, I think it's fine. Yeah.
Oh, is it?
It should be.
Okay. Okay, so Harry Bird is somehow, yeah, it's a different. Good. So now this aspect is the aspect that gives rise to the term glass. Okay. This term color glass condensate is weird, right? And somehow I wasn't that big of a friend of it when it was introduced by Larry. Now fine, I'm going to accept it. So this is a part of our explanation of why this is a color glass condensate. It's the color you can understand. We're talking about color all the time. So color in color glass condensate is fine. Condensate in some sense we will get to hopefully a little bit later today. But this is the feature that explains glass. So this is a glass, and somehow a glass, in some sense, the way I like to define a glass is that a glass is a liquid that flows so slowly that it looks like a solid. Now, this is not a proper definition for condensed matter physicists, but somehow a glass is a system that, while it does have some time dependence, the time dependence is somehow unnaturally slow compared to the time scale that you are looking at it. So if I'm looking at a drinking glass, I'm thinking about it in somehow seconds or minutes or hours, and those time scales, the glass does not flow. But some variety, at least older glasses, they do flow if you observe them on time scales for centuries, millennia. So glass is something that somehow has an unnaturally slow time evolution. So this is this feature is the color glass in the color glass condenser. Yes.
I don't think I really understood that last point about the small p minus implying. So is that another Heisenberg?
This is another Heisenberg and uncertainty argument. Small p plus. So therefore, weak x. So small p minus weak x minus weak x plus dependence.
So p minus.
So
the small p minus is also not changing a lot.
it is small. Well, it doesn't matter if it changes a lot; it stays small. So somehow, in some sense, the Schrödinger equation for my operators, or the Heisenberg equation of motion for my operators, is that the derivative with respect to x plus of some operator in the Heisenberg picture is plus or minus I, the p minus operator commutator with my operator. And if the p minus is small, then the evolution in with x plus is slow. And I'm approximating slow with 0. Okay. So that's the color. That's the color glass condensate.
Sorry.
Yeah.
Coming back to the nomenclature, in that equation that you've underlined, are we interpreting x plus as a time?
Yes, we are thinking about x plus as a time. Yes. But it doesn't, you don't have, you can think it's x plus. So if you don't want to think of it as a time, you just think of it as x plus. But it's convenient to think of it as time. This is why I switched x plus to x plus and minus, because x plus is the time in light cone condensation somehow conventionally. And somehow one is used to thinking of x plus as a time. But I mean, you don't need to care, it's just a word. I mean, this is the equation is what matters.
Why precisely is it that our source doesn't depend on the x plus?
So again, these two explanations, we are approximating. This is an approximation, the high energy limits. It's on one hand, one can say that it's time dilated. So time is time. So time dilation means that the Lorentz boost to a frame where this guy is moving very fast makes this a frame where its dependence on x plus is slow. So the Lorentz, that's what happened when you Lorentz boost to a frame where your stuff is moving. One can also think of it as an uncertainty argument. This is large p plus, so it is small p minus degrees of freedom, and because p minus small, they evolve in x plus slowly. And when slow, we will approximate with not evolving at all.
Right, but then why is it that we have a small p minus degree freedom?
Because we decided that this current is going to describe things that have large x, meaning large p plus, and p minus is some transverse momentum scale divided by p plus.
Okay.
They are all, it kind of goes together with large p plus, and there is no large p plus transverse momentum scale present in the problem. These are valence charges. They somehow there's some non-perturbative QCD effects that give them proton mass, and maybe they have some motion of the order of lambda QCD transverse momentum with each other inside the nucleus of the proton. But there's nothing that would be 100 GeV transverse momentum. So we can assume that because there are no particularly large transverse momenta present in these valence quarks, we can assume that if we boost them to large p plus, they will also have small p minus.
And this is because our target is on shell.
It is on shell, yeah. Or some of the proton is on shell. It's a proton that is on shell. The constituents of the proton or the nucleus maybe have some. They have some wave function. They have some motion, but this is motion at the order of hundreds of MeVs. It is not a large.
at this point, like in proton collisions at the LHC, like we also have said that the color glass condensate is broken.
Yeah, and that's exactly what you should be doing, at least if you're considering semi-hard particle production at 1,2 GeV. That's precisely how you should be thinking of the protons at the LHC. Good. Now let me put these ideas into equations, and we will write equations. So we have a J plus that depends on x minus and x perp, not on x plus, and it's going to be given approximately by a delta function in x minus. So it's going to be very peaked in x minus, and then it's going to depend on some color charge density transfers. So these, of course, all of these have a color index, and if you in the matrix notation, there's a color index and a generator. And I will just write it like this as a matrix, but I have to remember there's a color index. Good. So what this now means is that also A plus from this equation, I will write it a little bit formally as nabla per squared rho of x perp, and then a delta in x minus. So I write this kind of a 1 over nabla squared. What that means is just that this means that the solution of this equation, right? If I Fourier transform this equation on both sides, and then I can invert 1 over k squared, then I Fourier transform back, I can solve this equation. So this 1 over nabla squared is the formal notation for solving this equation. Okay. Oh, and let's calculate one more thing. Where is the energy of these gluons? We will calculate the energy of the field strength tensor F plus I, which is now, you have to be a little bit careful. We have well, not that careful actually, A plus. So this is actually, it's anti-symmetric. I move the index I down. So this is VI A plus. So this is delta x minus and di 1 over nabla squared rho of perp. So now I have dealt with the longitudinal degrees of freedom. I have reduced things to a transverse. I have reduced things to a transverse color charge density on the transverse plane of this accelerated sheet of color charges. Good. And so what this means, so if you remember, so I have an F, the only component of F mu that is non-zero is the F plus I. And if you think a little bit about the components, what this means, so remember that plus is a T component and a Z component. So if I go to X, Y, Z, T coordinates, this means that F has a Ti component, so that's a transverse electric field, and F has a Zi component, so that is a transverse magnetic field. So this is the field strength tensor of, actually it's a Weizsäcker-Williams field. It is the field strength tensor of somehow a charge. It's the field strength. It looks like it is a field strength tensor that looks like the field strength tensor of a gluon going in the Z direction, because it has components, electromagnetic components perpendicular to the axis of motion. It's the Z axis. So it kind of looks like a cloud of gluons accompanying, following this color charge. If you look at field strength. If you look at the field strength tensor. Good. So this is now our CGC color field. This is a CGC color field in the covariant gauge. because I have a covariant, I have a conservation of my current, and kind of the current, in some sense, the current and the field are proportional to each other. So this is a covariant gauge. And now you also recall that yesterday. So yesterday we were looking at the scattering of some dilute probe of a classical color field. And yesterday we came to the conclusion that A minus is the only component that matters. And now remember that we switched axes. So this is precisely the component of the gauge field that matters if you send now a dilute probe the negative direction to hit this color field. So this is the component that such a dilute probe will measure. Okay. But we do not like this gauge. We can go to a different gauge. Why? So there's several reasons. The most important reason for me is to go to the collision of two of these things. So we want to gauge transform to light flow gauge. And there are several reasons why raise the picture. There are several reasons why we would do that. So the first practical reason is that I'm going to need the light cone gauge field. I'm going to need the light cone gauge field. Another reason is that is related to kind of understanding if one wants to relate this field to one second. One wants to discuss this field in terms of a gluon distribution. Yes.
Sorry, is it in the plus component of the gauge field since every one of them is 0?
No, we'll see. We'll see.
Yeah,
when you're gauge transforming, you just move the stuff to a different place, and we will see explicitly how this happens. But first let me somehow try to justify why we need to. So I'm going to leave it in the calculation tomorrow. If I like to do light cone quantization. So if I would really do a quantization of this field, I would like to do it in the light cone gauge of this field. Somehow the light cone gauge of this field is really, in some sense, where you have a good parton. In some sense, partons exist only in light cone gauge. Now, you can do, and typically, if you actually do high order loop calculations in collinear factorization, you don't do them in light cone gauge. You do it because high order loop calculations are difficult in light cone gauge. But in some sense, people like that. In order to have a physical interpretation for what partons are, you really should be in light cone gauge. One reason is that formal reason is that if you want to define parton distributions as 2-point functions of some field, in order to make this 2-point function gauging, and you want the partons to have the partons having a specific p plus. This means that the 2-point function has to be non-local in x minus, which means to make it gauge invariant, you have to put a gauge link. And so when you put a gauge link, your 2-point function of quarks, for example, is not anymore a 2-point function of quarks. It's a complicated object involved with quarks and gluons. But if you choose light cone gauge, the parton distributions are just 2-point functions. So in some sense, the statement is that it is in light cone gauge, only light cone gauge, that you have an interpretation, physical interpretation of a parton distribution as a number density of particles, called partons. So it's good for the calculation we're going to do tomorrow. It is good for interpretation in terms of partons. One of the things that it's good also for our space-time picture, because now I erased. Just erase this, but this covariant gauge field, you see that our J plus was like a delta function on the light cone. So this is the covariant J plus, but also our A plus, our gluon field, was very localized on the light cone. And it was a delta function on the light cone. And this is a little bit contradictory with the justification for what we gave for this x minus, which said that the current is a delta function in x minus because it represents the large p plus degrees of freedom, which are localized. But this field is supposed to represent the small p plus degrees of freedom, and the small p plus degrees of freedom should not be localized in x minus. But this field configuration is. So in some sense, I cannot really, the A plus field having the physics in the A plus component is not good for quantization. It's inconsistent with kind of the Heisenberg uncertainty principle argument of where these gluons as partners should be. They should be small p plus things, which means that they should be delocalized in x minus. And in this gauge, they are not delocalized in x minus. So we want to see what happens when we go to A plus equals 0 gauge. And a little bit suggestively, you know how to do gauge transforms. A little bit. Well, let's do a gauge transform. What happens when you do a gauge transform? So in general, when you do a gauge transform, your A mu field goes to, I will suggestively write this as V dagger A mu V. So you first of all rotate in color space your original field. And then to cancel things out, you have to add a 1 over G times V dagger D mu V. And different V's correspond to different gauge transformations, right? And this is how you gauge transform a gauge field. You color rotate the gauge potential, and then you add a derivative. Okay, so let's do this. So we want to transform A plus 2. It goes to V dagger A plus B minus I over G. This is a plus up, so it's going to be a minus down. So B dagger B minus B. And we want this to be 0. Okay. This is the gauge transformation that gets rid of A plus. So here we can easily solve this equation. First of all, we can multiply from the left by B, move the things to the other side. And what you quickly recognize is that this is nothing but the Wilson line. So B is path order exponential of integral from somewhere up to x minus dy minus IG, I think the sign is A plus. This is exactly the same Wilson line that we had yesterday, except if you remember the which plus and minus. Okay, so the same Wilson line that is the iconal scattering amplitude of some particle to scatter of this color field. It is also gives the gauge transformation parameter that takes you from the covariant gauge to the light cone gauge. Okay. So then what happens to the other components? So A minus, we started off from A minus being 0. And so this term in the gauge transformation is still 0. The gauge rotates 0, you get 0. The other term is A minus up means plus down. And now nothing depends on x plus. So derivatives with respect to x plus are still 0. So which means that A minus still, A minus is goes from 0 to 0. A minus stays 0 in the gauge transformation. So where does the physics go? The physics goes into the transverse components. So the transverse components transform from 0. Transverse components transform from 0 2 minus I over G, this same Wilson line, and then DI and plus, because this is minus this is takes this down like this. So this is now my gauge field. It has in the light cone gauge, it only has transverse components. Okay. Let's look a little bit about what this does in space-time. So how does this, so you remember that I wrote this approximate here. So this means that this is not exactly a delta function, but it's something that is very peaked, right? So it means that the covariant gauge field is almost zero here, and zero here, zero here. It is only non-zero in a very small interval here. So what I'm doing when I'm taking the Wilson line, the Wilson line goes integrating over x minus from minus infinity to plus infinity. So here I'm just integrating zero, exponential of zero. So the Wilson line is so here the Wilson line is just 1. Right? And then here there's something that changes very rapidly, but almost like a delta function. So in this path ordered exponential. So I kind of jump from 1 to something that is not 1. But then after I jump here, the Wilson line doesn't really anymore. It doesn't. It's again exponent. I'm integrating over 0 exponential of 0, so it doesn't change anymore that much, right? So the AI, the light transverse component of the field in the light cone gauge, is something that is 0 here. Then it very kind of close to discontinuously jumps from being 0 to being something non-zero, and then again it stops depending on x minus, right? This is the x minus now direction. So this in the light cone gauge, the transverse component, it is going to be like a theta function in x minus, then times something that only depends on the transverse coordinate. And the transverse coordinate is you take this, and what this is, let me actually let us write this. Okay, so
the indices on the last A is a
Light cone.
light cone, LC.
light LC.
Different gauges, so I kind of want to LC like light cone. So the light cone gauge field now, you see that where does the light cone gauge field live in the space-time diagram? The light cone gauge field lives everywhere here. It is very delocalized. So that kind of matches the physical interpretation in terms of Lorentz contraction that we started with. The gauge field, the gluon field, is supposed to represent small p plus degrees of freedom, and correspondingly, it is very delocalized in x minus. So this is kind of so it fills all of this space. It is something that in the jargon of the field is referred to as a transverse pure gauge.
It's not a pure gauge.
Because it's not really a pure gauge. Of course, there is some non-zero field physics somewhere, but it is something that you get basically in this region. You started off from vacuum, nothing, and you did a gauge transformation, which so the transverse components of the gauge field in this region, they are non-zero, but they are gauge equivalent to the vacuum. But you cannot somehow globally in the space-time, you cannot transform things to everything to be zero everywhere. You can transform some things to be zero somewhere, but then other things are non-zero elsewhere. And in this case, kind of this matches the physical picture that in the light cone gauge, there is a gauge in this region, there are transverse components which are gauge equivalent to the vacuum, but nevertheless non-zero, and we have to treat them as non-zero. And these are things that we can understand as gluons, small x gluons. They are very delocalized in P minus, in X minus, so they are small x. They are small x gluons.
It has a little bit the field of black magic since we started first saying, we use the Heisenberg uncertainty principle to get certain properties for this A plus.
Yeah.
And they said, but A plus is not physical anyhow, so now.
No, I did not use the Heisenberg for A plus. I used it for J plus, and J plus, those are currents, those are particles, so they are there. I can apply the Heisenberg answer. I can think of them as fermions, right?
Okay.
And then the other one was a solution of the equation. Yeah, the other one, then the A plus was just the solution of the equation, but it was a solution of the equation, but was unphysical in the sense that it didn't satisfy the Heisenberg uncertainty principle argument. And now we go to a different LC, the light cone gauge. In this way, the light cone gauge is a physical gauge. The particles satisfy the uncertainty principle.
So what does your gauge transformation do to the current?
So that's you still the current, of course, the way the current gets gauge transformed is J mu going to B J dagger J mu B. So the current is only gauge rotated. So if you want to do this carefully, and you were interested in the current, you have to take whatever row you had here, and if you want to go to light cone gauge, you are going to gauge rotate this current into something. It's still going to have just a plus component, because now this doesn't introduce any new components to the current. If you start with a plus component, you get a plus component. It is just a color rotated plus component, and then one has to. I think in some sense one has to come back to this when you say what you want this color charge density to be. In practical calculations, I think it's actually easiest to think in this following way, that I will work with the covariant gauge charge density, but the light cone gauge field. And if what I'm gonna do next is I will write down a model for what this charge density could be. And for practical purposes, it's best to think of that as a model for the covariant gauge charge density. There was a question?
So you said that A plus, it doesn't really look physical on the covariant gauge, but it doesn't seem to like fit with the represents one. But how can you? It seems weird that you just do a gauge transformation and then it all looks physical. Should you change the physics?
Yeah. So this is kind of.
It doesn't change the physics.
It doesn't change the physics, but it changes the interpretation. It changes the interpretation. So somehow things like cross sections are gauge invariant, but our intuitive understanding of physics is not gauge invariant, right? And things like a proton consists of partons, which are kind of quasi non-interacting particles. These kind of statements, or that the parton distribution function is a probability density of partons, and this kind of things, or that the small x gluons are small x gluons and therefore have a small p plus and therefore should be delocalized. These are kind of physics intuition ideas that somehow in some cases only work in a specific gauge, specific Lorentz frame, and somehow, and then ultimately in terms, you cannot solve things, you cannot solve quantum field, you cannot solve QCD from first principles without anything. Somehow you have to, sometimes you have to make approximations, build models, and making approximations, identifying good approximations, building realistic models that you can use. That is somehow helped by having a physical intuition, physical understanding of somehow what the problem is. And that physical intuition, physical understanding can look different gauges.
The point is that gauge transformations change the space-time dependence, the coordinate dependence of all these animals, right? So by doing wild things, you can smuggling fast oscillations into anything through a gauge transformation if you want to, or you can make things much smoother by a gauge transformation.
So one typical quantum mechanics example is actually that a thing like when you start quantum mechanics, they will tell you that the momentum p is a physical observable. But actually, when you couple it to a gauge field, this momentum p is not a physical observable. It's a canonical. It satisfies the commutation relation, but it is not something you can measure. The thing that you can measure is p minus e times a. This is the thing that an experimentalist measures in the laboratory, not p. But it's gauge dependent. Oh, p minus ea.
Oh,
Yeah. So this is the kinetic momentum. That is actually the thing that an experimentalist measures when they measure a momentum of a particle in the lab. Whereas p, this is a canonical momentum which satisfies the commutation relation, but it is not something an experimentalist can measure. Yes.
I'm just a bit confused on how V is not equal to 1 once you're past 0. Because V isn't a gauge that A plus is equal to 0. So why would it change? It's because of the delta function jump.
Oh, but because V all the time, so it does not, V does not change as a function of x minus. But the AI is, so V is, so here we have a V that is not equals to 1 and only depends on the transverse coordinate. Right? It's the integral over this shock wave, and then it only depends on the transverse coordinate. So therefore, it does not depend on the x minus, and a plus is 0, right? This derivative a plus is 0, but it does have a derivative in the I direction, which means that it leads to a non-zero AI, a per transverse gauge field.
All right.
In this region. Then so we have a transverse gauge field that goes from 0, jumps very discontinuously to something that is non-zero and depends only on transverse coordinates.
And there's a jump because of like delta.
It jumps because we're integrating over this whole integrating over something that is very peaked.
Just to clarify, when you started talking about the momentum modes, it doesn't be minor. I'm specifically dealing with the large Jochen X part of the target, right?
For the current, yes.
Yes. But I'm just a bit lost because after you do the gauge transformations, and then when you conclude it, you mentioned that all of a sudden now we're looking at the small x part.
Yes, that's the field. So two different, again, it's a separation. I have two kinds of degrees of freedom. I have large p plus degrees of freedom, which are the current. And I have small p plus degrees of freedom, which are the field. And since they're large p plus small p plus, their dependence on x minus should be very different. Charges and fields. Different p plus, different degrees of freedom, different kind of degrees of freedom, different p plus, therefore it should also have different x minus difference.
Just one more question. I suppose in a lot of literature, this light cone gauge is essentially shown as a gauge fixing condition.
Yes.
But I just explicitly don't see how this is a gauge fixing condition.
Well, a gauge fixing is a term you typically use in quantum. So gauge in a classical theory, gauge fixing is easy. In classical theory, I did a gauge fixing. I started from something which is non-zero, and I did a gauge transformation, and I decided that I will do a gauge transformation that will transform this to 0. And in classical theory, that's enough. In quantum theory, you're doing a path integral over all kinds of modes of the field, and it's a more non-trivial question of can you force all of these different field configurations that you are integrating over to satisfy the gauge condition. It's a more non-trivial question, but I'm doing a gauge fixing in the sense, I mean, here gauge fixing is more straightforward because I'm really changing to a gauge where the condition that I want is satisfied. So this is really explicitly fixing the gauge.
You start from a gauge field, and then you want to gauge transform that gauge field such that the result, the thing to the right of the arrow, satisfies a condition, and they determine the gauge transformation. You determine V such that this happens. So input is the condition you impose, namely that the plus component vanishes. That's the condition you impose.
You're requiring that your
And it determines V.
plus component in the light bulb gauge is 0.
Okay, then both the given question here. If you the gauge you start off with is there's only an A plus.
Yeah.
But is it important or is it important whether this is not this is uniquely nailed down the page? Are the many gauge equivalent?
There are, because you can do infinitely many gauge transformations. In some sense, the only reason I ended up with an A plus was that was the starting from this current, which I put in. This was the easiest way for me to find a solution to the equation of motion. But of course, that was just one solution to the equation of motion. By doing a gauge transformation, I can find other solutions to the equation of motion. So kind of, I started with this for two reasons, because it is the easiest way for me to solve the equation of motion, and two, because this is the field that appeared yesterday. But there are, you can gauge transform. If you find a solution, you can gauge transform that to other gauges and find other solutions in other gauges.
Yeah, but I mean, I'm just saying it's the only one way to get the A plus and nothing else.
It's a second order differential equation. So given some enough boundary conditions, the solution is unique. So I found this by finding a solution. And I think if you specify enough boundary conditions, it will be a unique solution up to gauge transformations. So I think, of course, we can probably find other solutions, but they will satisfy some non-physical boundary conditions.
Let's come back to this in the title. You've seen things like this already in electrical, for example. So let's then.
Good. So let me just state one more thing, and then we'll take a break, and then we can maybe calculate something. Well, now the next question is, what is this rho? And somehow, in order to be able to calculate and get numbers out, I will now postulate a model for this rho, which has a lot of good, nice physical ingredients, but it is nevertheless a model. But it's a very reasonable model that has the advantages of A, allowing you to calculate a lot of things, and B, making a lot of sense in terms of physics. Okay, and so this model is the Maclaurin-Venugopouin model. MB. And the MB model is such that these color charges rows are a stochastic. So they are random variables, but they are stochastic, so they are taken to be random variables in a classical probabilistic sense. So kind of here, there's a delicate argument that I don't know to which extent one can say that it's proven, but there's an argument that somehow the some kind of quantum interferences coupling the small x and large x degrees of freedom don't matter. And of course, the large x degrees of freedom that are my color charges are some kind of, they are quantum physics. There is some quantum fluctuation. There's a wave function for what the color charges are of valence quarks. But somehow the conjecture, we say, is that the small x physics, the small x fields don't really care about somehow the interference effects, but they only care about the fact that there is some color charge that is a little bit fluctuating, can fluctuate from event by event, and can be taken. So we are treating it as a classical stochastic variable. Okay, so it's stochastic, and then we'll take a minimalistic approximation for how it depends on this x perp, and actually also a slightly delicate point is x minus. I've been insisting that it's an approximately delta function, but you need to regularize things, you need to spread it out a little bit. So we will assume that they are also local in x perp and x minus. So concretely, we will assume that the color charges, these color charges are stochastic random variables that are completely characterized by a 2-point function. Rho color component A, rho color component B, y perp, and y minus this are, let me check what my content, different people have different conventions of G. So I'll call this G squared delta A B mu squared and delta of x minus minus, let me make a little bit, mu squared of x minus, only x minus, delta of x minus minus y minus, and 2-dimensional delta of x perp minus y perp, like this. So I will assume that they are stochastic variables that are Gaussian. So what does Gaussian mean in this case? Gaussian means that if I tell you the 2-point function, you can calculate any endpoint function, endpoint expectation value from the based on the 2-point function. Gaussian, the word Gaussian here means that any endpoint function is given by the 2-point function. There's an established procedure for how you can calculate the expectation value of a product of 57 rows. Oh, and of course, in the sense of color, the only kind of color singlet thing color singlet 1-point function that you can have is, that they will be 0 on expectation value, but there will be a non-zero 2-point function.
So the statement is also that all odd endpoint functions are gone.
Well, yeah,
All
it kind of it follows from the statement
Gaussian.
that it's a Gaussian and the same 1-point function is 0. It follows that all odd point functions. So this is a very simplistic. So, but the physical picture here is that, okay, so this represents valence degrees of freedom. It's a collection of it's a collection of color charges, which I'm going to take as, I don't know anything else. I'm going to take them as point-like and completely independent of each other. So in some sense, it's a very minimalistic assumption. The other kind of way you can justify this, the Gaussianity, is you can apply the central limit theorem. I think that one way to state it is that if you take A going to infinity, if you take an infinitely large nucleus, which is also infinitely thick, there will be many color charges in the different nucleons, valence like degrees of freedom, that don't know about each other. And if you add up the color charge from many individual color charges that know nothing about each other, central limit theorem says that the distribution, probability distribution of color charge will be Gaussian. So it's a very minimalistic assumption. It involves, here I write it as a function. So this is it's a narrow color charge on this very narrow sheet. And so what will actually really matter is the integral. The only thing that will matter for physical observables is the integral of this mu, right? So which I will call as mu squared. So it's a simple model, kind of minimalistic model. point-like color charges that are there are many point-like color charges that are independent of each other. It has only one phenomenological parameter, and you can calculate all of stuff with it. So this is those are the advantages. Those are the advantages of this of the MV model. So let's now take a 10-minute break, and then we'll try to calculate a few things in this MV model. Good. So now we have a model. Now we have a model for calculating things with this MV model. So let's calculate things, and let's calculate. We don't have that much time, so we're not going to do it in excruciating detail. But let's calculate the dipole amplitude. I have written it down in my notes relatively in detail, and I'll try to not give you enough that you can somehow hopefully understand how this is done, but not too much, because my chalkboard writing is relatively slow. So what we are going to calculate this, let's call it D, which is 1 over MC trace the V dagger of X perp, V dagger of Y perp, where B is this Wilson line, and let me integrate to infinity here. Okay. So here, I mean, everything is there. And of course, we have expectation value, so we want to calculate the expectation value of this thing in the sense the expectation values of the MV model, right? So this is everything is there, right? You know what B is in terms of A plus, you know what A plus is in terms of rho, and you know what the 2-point function of the rows is, and you know any higher point functions because rows are Gaussian. So everything is there to make an explicit calculation of this thing. Good. So let me try to do this. Well, I want to really let me not do the calculation. Somehow discuss the ingredients of how you do the calculation. So here is the point where this is the point at which we still need to a little bit keep this somehow X minus dependence a little bit explicit. It's going to be very peaked, but not exactly a delta function, because the following stage of the calculation, I don't know how I cannot do if it's exactly a delta function. After we do this calculation, we can always forget about this X minus dependence and just consider the integral integrated over X. So take the delta function X minus literally. But at this point, this is the point. So first of all, let me just introduce a little bit more notation to make it shorter. So we have a 2-point function for the rows. We have a 1-to-1 mapping for the A's. So let me just introduce a notation for the 2-point function of the A pluses minus X minus and A plus covariant at Y perp and Y minus. So this is going to be delta AB, delta X minus minus Y minus. This is just the Y minus dependence just carries over from here. And then minus, and then some function of X perp minus Y perp, which is basically kind of the inverse Nabla squared Fourier transform back and forth. So we can calculate this function explicitly a little bit later, but for now we don't need it. We don't need it yet. So then the next thing to realize is that it is to do this calculation, we're going to have to we're going to want to discretize the X minus direction. Okay. So we will discretize X minus. so that we have some small delta x minus. And this is actually one of the, when things about path ordered exponentials that they don't necessarily always teach you when you are first introduced them. In some sense, the best way to think of a path ordered exponential is as a product of infinitesimal path ordered exponentials. So when we discretize this x minus, we are going to write this path ordered exponential, this b, as a product where we start with the exponential of, where we kind of discreturn this integral in the exponent to a sum, and then because these are path ordered, the path ordered exponential of a sum is actually an ordered product, right? So we are going to turn this into this is our exponent I g a minus a plus, I mean dot here at some x minus, and then an exponential of I g a plus x minus plus because I need to have a delta x minus, and then the next one I g a plus at x minus plus delta x minus and dot and times dot. And here there's also a dot times thing. See what I mean? So we somehow turn the integral into a sum of delta x minus times the integrand, and then because it's a path ordered exponential, the path ordered exponential of a sum becomes a path ordered product. So these are kind of, it's an ordered product, right? And then here I am of course going in the wrong direction. I think I changed my direction from yesterday. This, so let me change this to minus. Now I'm going the same direction as yesterday, so the later times are at left, right? Okay. So now my path ordered exponential is a product of an infinite exponential of an infinitesimal piece of the integral times the next infinitesimal piece, or the previous infinitesimal piece times the previous infinitesimal piece times the previous infinitesimal piece. Okay, I'm going to do the same thing for the b, and then the other thing to note is that I'm calculating b dagger, not bb, and that makes a huge lot of difference. BB dagger is a singlet operator. BB would not be a singlet. I would not get a sensible result for the non-singlet, but this is a singlet operator, and I get a sensible result for this. Okay. And the essential, in terms of this discretization, what happens is that when the BB dagger, in the BB dagger, the ordering is the other. You're taking a Hermitian conjugate, so the ordering turns around, then turns over. So here, if it's the later times at left, in the B dagger, it's going to be the earlier times on the left. So we're going to have an x minus delta x minus here. And then there's going to be the term at x minus. And then the term at x minus plus delta x minus. And so on. So we're going in the other direction. So this means that when I plug these two in here, and I can start, for example, from the middle, right? I start from the middle. When I start from the middle, from this b, I take the very earliest x minus, which is to the right. And from the b dagger, I take also the very earliest x minus, which for the b dagger is to the left. So I'm not commuting these. I never need to commute these to get them next to each other. But here I will just start from the middle, which is the start from here, which is the earliest x minus here and earliest x minus here. Right? And then remembering that these are the expectation values are local, what I'll do is that I'll take the earliest x minus, which is at the next to each other here. I use the expectation value, it becomes a scalar, I pull it out. Then I go outward and take the next ones. They're next to close to each other. I use the expectation value. It becomes a scalar. I put it out. It's a scalar, just a number confused with everything. And so on. So I do this piece by piece, this expectation value. And this is how I'm able to calculate it. So the next thing that I need to tell you is what happens with this expectation. So I'm taking one single piece here. Was there a question? I'm taking a single piece like this. So I have an exponential of I G A plus and delta x minus, right? This comes from the V. Then from the V dagger, I have the minus I G A plus. Okay, so this is at x. This is at y. Delta x minus. Okay, so now delta x minus is infinitesimal. I can expand. Right? I need to expand to quadratic order. And I remember I'm taking the expectation value here. Yes.
For the term on the right, why is it? Should it be a delta x or should it be a delta y?
Delta y. Yes. Well, yes. So x minus, but it depends on what you can call it, and you can call it the delta y. You can kind of discretize this with delta y minuses. But then when you're taking these pieces together, all the expectation values always there's a x minus and x. When you're taking the expectation value, x minus and y minus are the same. So I'm just writing delta x minus everywhere. It's just that somehow I could call this delta x minus epsilon. It's the size of my step.
Okay, and these will
It's the size of my step. So let me write this a little bit more carefully. This is a plus at x minus and x per delta x minus, and this is at y minus y per and delta x minus. So delta x minus is just a constant, which is the size of my step, right? But this is at y minus and this is at x minus. But I'm going to use this expectation value, and they become x minus becomes the same as y minus. So I expand, I get 1, then I get minus IG a plus, but plus IG a plus minus IG a plus. The linear terms from here and here, but they vanish. The expectation value of the 1-point function expectation value is 0. Then from here I get minus 1/2 a factorize this out plus g squared delta x minus squared, and from here minus 1/2, and then I already have. Let me just take the expectation. So a plus squared. I'm using this notation for the expectation value, right? I have discretized this x minus, so I'm not going to write the delta function. So I'm somehow already dealt with it, but I have this L, and here I have it's the squared. So it's this L, it's this function L at 0, at argument 0. Then I have the square term from here, which is also minus 1/2 L and 0. And then I have the plus I and term from here and the minus I term from here, right? So it's a contraction between these two a pluses using this. So that gives me a plus L at the correlation function at x per minus 1. And then there is this times there's a delta AB, and here I have a color index A, and I remember that here this A is a color index A and times TA. So I use the delta AB to contract the color indices of the gauge, individual gauge components for delta AB, and then I'm left with this tail PA. This one is a B, so these survive. So PA B, which is nothing but CF. CF times the identity matrix. Okay. CF times the, because these are all matrices, but this is a CF times the identity matrix. And then I have expanded these V's into pieces that are multiplying each other. I do the same thing for, I do the same thing for every piece. Now the additional thing, now delta X minus is infinitesimal, right? And actually what this, I have a delta X minus, but here I have a delta of X minus equals 0. I mean, somehow sloppy with these notations, but this this delta, when I discretize, this becomes a 1 over delta X minus times Kronecker delta. Y minus, so the continuous delta function becomes 1 over the step times the 1 over something that goes to 0 times the Kronecker delta, and Kronecker delta is 0. So that actually cancels the square here, and I get something that is proportional to 1 power of the time step. And then I actually, since this is infinitesimal, I can re-exponentiate. This is again equal to exponential of g squared delta X minus, and then I have this. I think I have this mu squared here. I forgot. So squared, and then you see this combination. I will call. I think I will call it minus gamma of X minus y. But it's essential that this is -1/2 minus half 1/2 plus L, because our correlator L comes from this Gaussian equation. The correlator L will be very, very divergent at the limit of 0 distance. Correlator L, the L at 0 will be something that has to be regularized in this power law divergent. But in this, the correlator L appears in this combination where the value at 0, and then the value at non-zero separation come in this combination, which cancels the leading short distance singularity in this correlator. And this happens because and only because we are calculating a color singlet operator. It happens because we had to have a plus I here and a minus I here, a B and B dagger. Right? We're calculating color singlet, we get a sensible result. We get something that is regular, as we can see if we calculate this. If we calculate this more carefully, and I put a minus here, see that gamma of X squared minus y. So, and then I put all of these together. So this I do for, remember I was starting from the middle. I do this for piece by piece, going from early time to early X minus to late X minus, always kind of taking little pieces of these exponentials, putting them together, taking the expectation value, re-exponentiating like this. Then I take the next pieces, I do the same thing. All of these are proportional to, there's an identity, NC times NC identity matrix here, because these are all the time matrices. And since they're identity matrix times this kind of an exponential function, the identity matrix is commute, and I can just pull everything out. Yes.
In the V that you have, the popular explanation.
Yeah.
Gauge fields are okay, what gauge are they in? Covariant gauge?
This is the covariant gauge field, which is the one that is in the exponent.
So, the solution to that, if I remember, came with the delta matters.
Approximately delta, but I maintain that it is something that is very peaked. But until this stage, I need to keep it. To make sense of this calculation, to be able to calculate this, I cannot really take it to be exactly a delta function. I need to spread it out a little bit.
Okay. So I'm just curious.
No. And that the reason I need to spread it out a little bit is precisely because of this, because in order to calculate this, I need to discretize these Wilson lines into piece, infinitesimal piece times infinitesimal piece times infinitesimal piece. And therefore I need to have it smooth enough so that I can splice it, split it in
So
little
that you
pieces.
have pieces, right? Otherwise there's nothing to slice.
So it's very peak, but not exactly a delta function, because I need to somehow spread it out, discretize it in x minus in order to be able to calculate this expectation.
So what problem do you run into if you just put in the delta and the
If you put in the delta, you cannot. If you put in the delta, so it's a question of you have an integral like this, right? Which you approximate as the sum over n, some delta x times fn, like this. Now, if this is a delta function, your fn's will be some of these fn's are going to be either 0 or one of them is going to be infinite. And if you have one of the fn's that is infinite, even if you're multiplying it by a small delta x, if this is infinite, the delta x times infinite is not small. And then if it's in the exponent, you cannot expand the exponential. So in order to be able to expand this exponential, I need that when delta x minus is small, the whole exponent is small, and that doesn't happen if the n pluses are infinite.
but you do the integral.
You can do that, but I need to do the integral as a kind of as a discrete sum approximation. And for this, I need to somehow smooth it out a little bit. Good. So the final result. So okay, so the identity matrix, which in the end pulls out just two as then this trace gives an NC, it cancels the 1 over NC. So what I get here is an exponential of yeah. Well, here it's g times a plus. Here I have a g to the 4 because the g's don't really matter that much because everybody has them all over the place. But I had a 1g times a in the exponent, and then I have another g squared in the expectation value. So altogether, it's g to the 4. Different people have different conventions here, so it doesn't really matter that much. I will have exponential of g to the 4th CF. Right? Then now this became going to delta x minus 10 times this mu squared, this color charge density parameter at x minus. So I have then I multiply these back together, then the multiplication of exponential times infinitesimal becomes a exponential of a sum, which I again write as an integral. So dx minus mu squared x minus here and gamma of x per minus y per, right? Okay, so and at this point I can forget about this discretization x minus. Everything just depends on the integrated color charge density. When you go through the whole thing, you accumulate the integrated color charge, and after you come out, the only thing that really matters after the end of the calculation, the only thing that really matters is the accumulated total color charge that you got going through this delta function. So at this point, if you want, you can say that this is a delta function, the x minus, and I integrate the residual function, it's a number. After doing this expanding the Wilson lines, taking expectations and just resumming back, I get this. Okay, so this is our dipole amplitude. Let's calculate.
Maybe you guys want to know what happened to the NC. Trace of 1.
Yeah, so every single piece of this is an identity matrix trace. In the end, after I take the expectation value, it becomes an identity matrix. Trace of identity matrix is NC, it cancels the 1 over NC. Okay. And now you see this gamma was explicitly constructed in such a way that when x perp equals y perp, this thing is 0. Okay. So when x perp equals y perp, this is 0. It's exponential of 0, which matches with the fact that when x is equal to y, BB dagger in identity matrix, and you should be getting 1 for this. So it's that somehow part of the thing is consistent. You don't get such a consistent thing unless you kind of re-exponentiate like this, expand and then exponentiate again. So what does this gamma look like? So this L of x perp minus y perp. So remember that our starting point is that the L is the correlator of A pluses. A pluses are 1 over nabla squared rows, and the correlator of 2 rows is a delta function. Okay. So how do you calculate it? You Fourier transform. I Fourier transform this. When nabla squared becomes 1 over k squared, and then I need to Fourier transform back. So the L is basically a Fourier transform for d squared k perp over 2 pi squared exponential of k perp dot x perp minus y perp over k to the 4, right? Because it's a 2-point function of things. I mean, in both of these 2-point functions, I have an nabla squared. Very sick, very, very sick. Right. And so, yeah. So what is this? This is where the subtraction by. So first, of course, this is very infrared sick, right? So I have to put somehow regulate the infrared here by some lambda. There's a term that goes like. 1 over lambda squared, completely power law infrared divergence, but that cancels when I subtract the value at 0 separation. It's kind of funny that this here is always confusing here. It's a small momentum divergence, and then a short distance. It's a short distance behavior. There's a short distance subtraction. You would think ultraviolet. So is this ultraviolet or infrared? I don't know. I have trouble somehow interpreting these things. And this comes all the time. In this somehow, I have trouble getting an intuitive feeling for whether I should be thinking of this as infrared or ultraviolet. So anyway, the leading contribution cancels when you take this separation. But then there's still a logarithmic contribution, logarithm that is left after one does the calculation, after one subtracts this. So overall, in the end, one can do a calculation and regulating somehow, and of course the details depend on how you regulate it. But in my way of regularizing, which I don't even remember what it is, these notes is what I get is 1 over 8 pi and r, so I mean is x perp minus y perp squared log 1 over x perp minus y perp times some lambda. Okay, so this is an short low momentum regulator. So this is an expression that is meant to be good for short distances. This is why I write it as 1 over log, because this this r times lambda, or this x per minus y per times lambda is supposed to be small. This is a long distance regulator. So 1 over this small number is a large positive logarithm. So in this, written in this way, this is positive. And so what I have for the dipole correlator is exponential of minus color factor. This is fundamental representation. I'm writing this fundamental representation. I use our fundamental representation matrices, so I get a fundamental Casimir. Some integral over the integrated color charge density of the target over my line of motion for the Wilson line, times some function which goes like r squared, and then a log. So of course, it's r squared times a log, and somehow if you plot it in coordinate, and if you plot this in coordinate space, the log matters very little. So what is this looks like kind of precisely what we were drawing. If you plot such a function, it will start at 1. This becomes 0 at r going to 0. I mean, some of the log is not strong enough to make this into being non-zero at r equals 0. Right? So it still is exponential of 0 here, and then it's r squared. It grows. Well, if you take this log seriously, you're not supposed to go infinitely far, but at least if my 1 over lambda is somewhere here, it's very, very long distance. This is r, which is x per minus y per. I start with 1, and then I basically go to 0. Maybe after this cutoff, there's something crazy, but that's somehow confinement scale difference. I don't care. And this is, so it's like a Gaussian. It's like a Gaussian. And here again, you see that, okay, we decided that we were going to have our saturation scale is somewhere where this is not, somehow where it's the limit between close to 1 and very much smaller than 1. There's some characteristic scale which we call the saturation scale. So now we can kind of identify that this essentially is our saturation scale, depending a little bit about what different conventions about fusion. I mean, but it's a characteristic scale. There's no unique definition. You can have somebody defines it with a factor 2, somebody else with a factor 5. But basically, what you see is that we have this behavior where the Wilson line correlator has a perturbative like. So here the perturbative like is 1 minus r squared, maybe times a log behavior, short distance, but then it does saturate to like 0. Saturate, if you want to calculate the amplitude would be 1 minus this. So the scattering amplitude would be, this is 1 minus the dipole. This is the dipole. This is the perturbative regime, and then here is the saturation. Here's the saturation. So we see that the saturation scale, it is a momentum transverse coordinate scale or a momentum scale, and it's related to the color charge density. Well, it's related to the color charge density in the target. So it is given by that. Given by the color charge density. So one thing about the thing about the log. So often this log is approximated by just a constant. People leave out this log, then this becomes a Gaussian. That is known as the GBW or Golec-Biernat-Wüsthof model. That you throw out this log. In coordinate space, throwing out this log looks very innocent. But it matters a lot when you Fourier transform this. It's a function and plot some kind of an unintegrated distribution as a function of k. I will start at some k, some constant here, And if I forget the log, it's going to be a Gaussian. But if I keep this log, it's going to be a power 1 over k per the 4th versus exponential of minus k per 12. So this log looks very innocent in coordinate space. In momentum space, it's a difference between a power law and a Gaussian. And somehow the power law one can go back to where the log comes from. The log comes from the fact that we were Fourier transformed this 1 over nabla squared. And the fact that we have a delta function here. So this log, this log in coordinate space and the associated power law in momentum space is associated with the fact that in this model these are point-like color charges, and it's the Coulomb field of two-dimensional Coulomb field of a point-like charge looks like this. Log in coordinate space and power law in momentum space. And then leaving out this log transforms it, leaving out this log at this point transforms it into something very different in momentum space. Both are used in phenomenological applications.
Well, the Gustav model was earlier, right? This was,
so this was
more or less an
didn't come like this. It was just postulated.
Yeah.
And but later many people have done this calculation and then said, oh, let's forget the log and we'll just use the
ages ago. Then Larry and I did this, and
yes, and you did this with Rummukainen too.
yeah.
They were managed to convince you to do something else.
What's special before the movie define one of the fields? Changes.
Well, different people define it in different ways. It is just somehow, it's a question of, this is a region when you are much less than 1. This is a region where you are just a little bit less than 1. Okay, and so we have to choose. Typically, you would choose some number between 0 and 1 and decide, okay, this is where. Choose some number here and decide that, okay, that's the point I'm going to use. But it's everybody has their own convention. Yeah, I mean, this is you are interested in experimentally measuring it, but before somehow quoting values in GeV, it is you need to specify which convention you have chosen, what exactly you mean by QS, right? And different people use different conventions. Also, there's a color factor here, so it depends on whether you're looking at adjoint or fundamental. What representation corresponds to the cross? I mean, the cross section of some particular process corresponds to some color particle in some representation, and you have to use the appropriate. You have to use the appropriate color factor. Good. So I think I'll say one more thing, and then not do a calculation. Then I think we can. I'm finished for today. So this is known as the by Fourier transform. This is known as the dipole distribution. We also had this light cone gauge. I can calculate what is known a Weizsäcker-Williams distribution. And I can calculate what function of these light cone gauge fields. Okay, and then let me add a color index. So this is known as a Weizsäcker-Williams distribution. So now, if you want, as I said, if you want to count gluons, you prefer to do it in light cone gauge. So this is as close as it gets to the number density of gluons in this heavy nucleus target at small x. If you somehow want to think of them really as quantized gluons. So this is a quantity you can. If you want to interpret as a number density of gluons, you want to compute this. It's doing a calculation that is a little similar than this, a little bit more complicated, but similar than this, you can do it. This was first done by, I think Heribert was involved with the first first time this was calculated, the result that you get looks, well, it's a little bit different, especially at low KT, but it does still exhibit the feature of saturation. It behaves in a different way at short distances versus long distances. You can identify a saturation scale. This, because there's now this A light cone gauge field is a pure gauge field, there's a 1 over the coupling here. And these Wilson lines are kind of order 1 in the coupling. Right? It's they're unitary matrices, they're kind of, there's no. So this means that this Weizsäcker-Williams distribution is proportional to 1 over alpha S. 1 over alpha S times then some Wilson line correlator, which varies between somehow 0 and 1, depending on how you are with the saturation scale. But when you're around the saturation scale, it is something that is of order 1. So this is the origin of the word condensate in the colored glass condensate. So if you really insist on trying to define an occupation number of number density of gluons, you can calculate it, and you will find that, and you somehow, even without calculating it, you see that it's proportional to 1 over the coupling. So that was my final point. I think this is enough for today.
Why can I think of a number density?
Because if you quantize, in light cone quantization, that this is what you quantize. It's if you quantize in light cone quantization, this is what you write, that the AI LC is an integral over invariant phase space, creation and annihilation operators. Creation and annihilation operators with K dot X, and then polarization vectors corresponding to physical polarization states, where the index of the polarization vector is this. Right? Then in light cone gauge, A plus is 0 and A minus is just a constraint. A minus is a dependent degree of freedom. A minus is something you express in terms of A. So if you start light cone quantizing this theory, basically you will say that my field operator is a sum over polarization, sum over phase space, creation and annihilation operators, exponential polarization vector, and converse conjugate. And then now if you have creation and annihilation operators, these tell you what the number density is. So then the number density will be a 2-point operator of these light cone gauge quantized field operators in some state, some harmonic state. And the classical approximation for this 2-point function of the operators is the 2-point function of the classical fields. So that would be this is why, if you want to define a number, but the point here is that the number density is not actually, this kind of a number density isn't necessarily the most useful thing in terms of in order to calculate a physical cross section. There are some cross sections that you can argue that are really sensitive to this distribution rather than this, but most of the cross sections we're interested in are actually kind of better obtained from this than this.
The different measurable quantities that have one or the other in them. And yeah, Bo and Charles have a fairly good paper explaining which is which.
And then somehow people doing kind of not doing CGC, but doing transverse momentum dependent factorization. In principle, you can write down a manifest gauge invariant operator definition for both of these distributions. In such about conventional perturbative QCD, these are just independent distributions that you have to independently measure in different processes, and they have nothing to do with each other. Right? Having something like the MV model gives you a model in which you can relate them to each other, and somehow increases the predictive power of the theory compared to just saying that these are independent, I measure them separately.
So when you talk about, gluon distribution, what do you have to do with the?
Well, when I talk about gluon distribution, it is, I use the word in kind of an illustrative sense, not in a quantitative statement. And
So
if you really want to choose, I think this would be better.
Are there more transfer information distributions than there are in Gigalab, right? In Gigalab, we have the structure functions. If you look at the transfer information distribution, we have different operator expressions that you can think of as relating to gluon number in some way, and they differ largely in the way you sum the gauge links between them to make the thing gauge invariant. So these gauge links actually matter, and the way you line them up, in the end, either get in the small x limit, either gets you to this or to that.
Yeah, so you can write and explicitly gauge invariant operator definition for both of these.
The transverse PDFs would have one more argument.
Yes, exactly. So these are the transfer coordinates, right?
And yeah, they have the transverse, but they also have the longitudinal corresponding to the x, which
X.
is now black.
Yeah, right. Yeah.
Then depending how you take this,
You get one or the other.
Yeah, and different processes depending on what the cross section is are expressed in terms of one or the other distribution. Like yesterday, we calculated the single inclusive particle production in proton nucleus collisions, and we saw that it's given by this operator. So that particular cross section is this operator. Like when Matt talks about inelastic scattering, he will write down the cross section in terms of this operator. But I think the statement is that digest production in DIS in specific certain kinematical regime would be more naturally expressed in terms of this.
So when you calculate some of this light bulb gauge, again, you have to tell me then what representation the colors are using.
Yeah.
And what I remember, you got this from solving classical angle. Yeah. So, yeah, what do you decide on that?
Well, in this, so here I was writing things in the fundamental representations. I was calculating in terms of fundamental. This is a fundamental representation trace. These are fundamental representation matrices. Yeah. But somehow this calculation carries over in any representation. It is just where did the representation come? The representation came. Actually, the color I had this thing for the color components, and then the only place the representation came is that I took this delta, Kronecker delta, and then I had the generators for the whatever representation I am in, and this was the some representation, and this was the Casimir of that representation times an identity matrix in that representation. So I can repeat this calculation in any representation. The only thing that will change is this Casimir. But I think if you're referring to what we were discussing yesterday, we were discussing classical color charges, right? So those classical color charges are something that they don't live in any particular representation. The classical color charges are what go into here. I have this mu squared parameter or the QS, this mu squared, and that's the sum of all the classical color charges in the target. I don't care what representation they are in. There are many. They are many in the MB model. I'm approximating that there are infinitely many. They are random variables. The only thing I care about is how much charge is there in total, because that tells me how many gluons. That tells me how much glue I have at small x. How much charge do I have in total at large x? And that's the only thing I care about. I don't care about whether the quarks or gluons or something else. I just care about the total number of color charge at large X. Good. So should we take a break? Should we take half an hour, 15 minutes?
Yeah, let's at least make a little bit of break. So thanks, Tuomas.